minus 0.00048, no unit. And then epsilon y will be equal to 0.001724. Okay, so we have this one. Then our answers, we want to calculate the strength, so that will be the dimensions. In x dimension, that is 1 times epsilon x, and this one will be 2 times epsilon y. Okay, the deformation, by definition, deformation is equal to strain multiplied with corresponding dimensions. Okay? And the next one is plane strength. And again, the plane strength problem is another category and another extreme scenario compared to the plane stress. The plane stress is assuming we have a model just like paper. The third dimension is very small. So again, in this section for the plane strength, and your job is to learn the definitions and then know the assumption or conditions. Then at the end of this one, you should be able to solve similar problems like this. Okay. Plane strain applied to the practical problems is like I'm showing here. If you consider this a long for example, if you consider this one as the water dam, okay, the structure for water dam, and one side is the pressure from the water, okay. So for this case, is the situation is for any model, it has one dimension that is very, very large compared to the other two dimensions. Once you have this model, then right away you could begin to justify whether this would be the good 2D model under the plane strain. Once you identify one dimension is so big compared to the other two, then you further to justify the loading conditions. The loading condition is just like this. You merge that, for example, the big pipe, solid pipe into ocean. And that pipe basically is under the hydraulic pressure, in particular is on the sides. Okay? So basically assuming this is a water dam. So that means the loading is uniformly applied along the sides. Under this situation, you can right away, this is fitting to the plane strain. So that means rather than model the three-dimensional big chunk of the models, we can just use two-dimensional sheet material, okay, and with appropriate modification in the material properties, then you'll be able to use this 2D model to simplify the complicated 3D. So under these situations, the information is this. In the real application of this one, if this situation has a one dimension, it's very large, for example, in this dimension, compared to the other two, and also is under the in-plane, we call the in-plane the deformation. Then the strain, that is a condition under which we're going to simplify the problem. Is this. The strength in the larger dimension, the strain in that dimension basically is very small. Because you could imagine, if we have a very long solid pipeline, the pipeline is under pressure from the sides. We squeeze it. The strain or deformation in the long axial direction actually is small. Okay, so that means the strain can be ignored. Okay, so that means, let me again pick up, this is the x direction, y direction, z direction. So all the strain components has z component will be 0. compared to our plane stress, we can see the plane stress is all the stress components with z equal to 0. The strain is all the strain component with z equal to 0. So that's the opposite side. Okay, so think about this one, and the best way for you to memorize the plane stress or plane strain, you just think about these figures. I think those figures and the previous one is the metal sheet, the sheet metal, that is a very typical one. Okay, so.
Wait, is it supposed to be that the strain in one direction is much less or much greater than the strain in the other? Like, in your words?
The strain in this direction is much, much less.
It's less.
Less. Because under this loading condition, because we don't consider axial loading.
Okay.
If we have an axial loading, then that's a different story.
No, I get it now.
Then under that situation, although this model is that kind of dimension, but if the loading couldn't be fit into this, then you cannot using the plane strain. Okay, so that is the kind of the restriction. Okay, so we're back to our Hooke's law again, and you can see this is Hooke's law for three-dimensional generic problems. And under this situation, you can see I rewrite the expression. This side is strain, and this side is stress, and from three-dimensional. And the contents, I basically rewrite everything, and that is the inverse of the previous one. You look at this one here. Okay, so that is our previous one. I place the stress here and strain on that side. I just do the inverse calculations. Okay, so now it's this, and now we have all the strains related, they involve the z equal to 0. So basically 1, 2, 3, those components with z, and that will be 0. So we'll put them into 0. So and then in this one I can rewrite everything a little bit more and into the simplified problem statement. This is a one unique box and for your calculations. And if you like, because right now I don't believe you have to print out this slide, and this is the one you can write it down. And for your plane strain, okay, for your plane strain formulations, and this one can be used for your calculation. I can give you 1 minute and for you to write it down carefully.